about the topic hybridization. Hybridization is defined as the mixing of atomic orbitals of the same cell within the same atom and forming new hybrid orbitals. While mixing these atomic orbitals, the atomic orbitals have similar energy and redistribution of energy takes place and forming the new form of the orbitals which are having equal and identical in shape. These formed orbitals are called hybrid orbitals. In an analogy, you can give one bucket of white paint mixed with one bucket of red paint. You will get 2 buckets of pink paint. The pink one is the hybrid. The same way your atomic orbitals mixing and you are getting the hybrid orbitals. So what is the necessity of formation of hybridization among the atomic orbitals? The reason for the hybridization is, we know valence bond theory has given the shapes of some simple molecules. It is unable to predict all the molecules shapes in a precise way. According to the valence bond theory, a covalent bond is formed. The off-filled atomic orbitals of the atom overlapping to form the equivalent bonds. While overlapping the off-filled atomic orbital to form a molecule, the direction of the overlapping leads to the bond formation and gives the shape of the molecule. But it is unable to fulfill all the molecules the shapes. As a result, we can see some of the examples of beryllium, boron and carbon which are not fulfilled by the valence bond theory. Beryllium atomic number is 4, boron is 5, carbon is 6, and its electronic configuration is configuration 1s2 2s2, and this is 1s2 2s2 2p1. In case of the carbon, 1s2 2s2 2p2, that is 2px1 and 2py1. While the off-filled atomic orbitals are intermixing to form the bonds which is equal to its covalency. As per the valence bond theory, the covalence of beryllium, boron and carbon must be 0, 1 and 2 as per its electron configuration. But in reality, the beryllium is having the covalency 2, the boron is having the covalency 3 and carbon is having the covalency 4. To overcome this difficulty, let us take the example of carbon atom. We will see how this problem we can overcome. And let's take the carbon atom atomic number is 6. Its electronic configuration is 1s2, 2s2, 2px1, 2py1. It is in the ground state level electronic configuration. As such, its covalency is 2, but in practicality, its covalency is 4. For this purpose, we can explain the paired electrons of 2s orbital is promoted to the 2p orbital in the excited state. In such case, carbon electronic configuration is 1s2, 2s1, 2p, x1, 2p, y1, 2p, z1. It is in the exercise 3. Now you had a 4 unpaired or 4 off-filled atomic orbitals. Now its covalency is 4. With these 4 unfilled atomic orbitals, the other atoms will form and form the 4 covalent bonds. Among these, one is the 2s orbital, which is having the spherical shape. The other one is the 3 are the p orbitals, which are having the dumbbell shape. While the incoming atoms react with the 4 off-filled atomic orbitals, their shape must be, one is different and the other 3 must be in the different shape. That is, all the 3 p orbitals are in the plane of 120 degrees, whereas the s orbital is different from that. But in fact, in reality, all the 4 covalent bonds of carbon atom is having equal tetrahedral shape, and their bond angle is tetrahedral shape, and bond angle is 109 degrees, 0.28 minutes. Now the problem arises as a result, and the scientists have developed the hybridization concept. In this case, what is happening is the 2s orbital and 3p orbitals of intermixing and to form 4 sp3 hybrid orbitals. If these 4 sp3 hybrid orbitals, the 4 incoming atoms will react and form 4 single bonds and forming a tetrahedron in shape. As a result, the failure of valence bond AB and this new hybridization concept was developed to satisfy all the molecules stretches, to know all the molecule stretches precisely and clearly. Now, in the hybridization, as I told earlier, if the hybridization between one s orbital and one p orbital, which are having spherical and double shapes, forms hybrid orbitals of same p orbital shape, but among the two groups, one is a bigger in size, the other one is smaller in size. Always the bigger size of the hybrid orbital shows positive symbol and the smaller one shows negative symbol. This is the s orbital, this is the p orbital, this is sp hybrid orbital. The shape of sp hybrid orbitals. Now, some of the important points about the hybridization. First one is only those orbitals which are having equally or approximately equal energies of the same atom must undergo the hybridization, and it is need not necessary all the off-filled atomic orbitals has to participate in the hybridization at the same time. Some of the off-filled atomic orbitals remain on hybridization of the same atom, or even completely filled orbitals also can participate in the hybridization process. During the hybridization, the number of atomic orbitals or reacting orbitals and formed hybrid orbitals must be in the equal, then there is no change in the number. And the hybridization indicates the geometry of the molecule. If you know the hybridization, we can say the shape or the geometry of the molecule. In the hybridization, the a hybrid orbital, the bigger lobe is designated as a positive and the smaller lobe is designated as a minus symbol. And the next one is the type of hybridization. Types of hybridization. The first one is diagonal or sp hybridization. In the diagonal and sp hybridization, one s orbital intermixed with one p orbital and to form two sp hybrid orbitals. One s orbital intermixed with one p orbital to form two sp hybrid orbitals. And these s orbital and p orbital belong to the same main cell. They are intermixing to form new two hybrid orbitals which are having almost same energy. And the s and p orbitals are unilinear and form a small triangle. The shape of this is this and this is this p orbital, and you get sp hybrid orbital like this. Its shape is 180 degrees, and wherever the sp is there, you can say its shape is 180 degrees. If 180 degrees are there, you can say its hybridization is, you can predict the hybridization as sp hybridization. Examples of sp hybridization is all your carbon-carbon bond compounds, like your acetylene C2H2, and your boron, beryllium chlorides, that is your beryllium chloride, beryllium hydride, etc. These are some of the examples of your sp hybridization. During this hybridization, some may be off-field orbitals may not go in the hybridization. They remain unhybridated orbitals. They react with other atomic off-field atomic orbitals. They form the covalent bonds. The next one is sp2 hybridization. And the types of hybridization. The next one is the sp2 hybridization. This sp2 hybridization, in other words, we used to call it the trigonal hybridization. Trigonal or sp2 hybridization. In this, one s orbital, suppose you can take 2s with 2p on the same cell. In the 2s you are having one s orbital, and p you are having, that is your px, py, pz. Two p orbitals, and this is s orbital undergoing the hybridization and forming 1 plus 2, 3 sp2 hybrid orbitals. The sp2 hybrid orbitals, the shape is in a planar, it is like this. This is the sp2 hybrid orbitals, and you have the unhybridized 1p orbital, and here the bond angle is 120. The unhybridized half-filled p orbital may react with the reacting atom and form